Experiment E20, Tripping Characteristics of Overcurrent and Leakage Current Protection Devices.
A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. Its function is to interrupt current flow after a fault is detected. Unlike a fuse, which operates once and then must be replaced, for a circuit breaker, it can be reset to resume normal operation, and it can be used many times. The circuit breaker is labeled with the rated current in amperes, but excluding the unit symbol A. Instead, the ampere figure is preceded by a letter B, C, or D, which indicates the instantaneous tripping current. That is, the minimum value of current that causes the circuit breaker to trip without intentional time delay. In this picture, the number of the circuit breaker is B6. So it means the rated current is 6 and the type is type B. So this is a type B 6M MCB. International standards IEC 60898-1 and European standard EN 60898-1 define the rated current IN of a circuit breaker for low voltage distribution applications as the maximum current that the circuit breaker is designed to carry continuously. And this current is for the ambient temperature of 30 degrees C. So in this picture, we have single pole MCB. So the MCB is used to control the live conductors only. And for double pole MCB, both the live conductor and the neutral conductor will be tripped. And this is a 3-pole MCB, and this one is a 4-pole MCB, which will also disconnect the neutral conductor. The instantaneous tripping current is the minimum value of current that causes the circuit breaker to trip without intentional time delay, usually less than 0.1 second. And the instantaneous tripping current IM is usually expressed in terms of IN. That is, how many times of IN. So for a type B MCB, the instantaneous tripping current IM will range from 3 times to 5 times of IN. And for type C MCB, IM will range from 5 times to 10 times of IN. And type D will range from 10 times to 20 times of IN. This picture shows a single-phase MCB board. You may find this in your kitchen at home. And on the right-hand side, this is a diagram showing the wiring. So this is the main switch, and we have different circuit breaker. And this is the RCCB, the residual current circuit breaker. And these are the MCB. And these MCB or these circuit supplied from the MCB will also be protected by the RCCB. So usually these circuits will be for the socket outlets. So in this experiment, we are testing the time current characteristics of these 3 MCB. The brand is Schneider.
So we have the MCB type B 6M, type C 6M, and type D 6M. These circuit breakers have different types B, C, D, but they have the same current rating of 6M.
For the equipment, we are using this mega high current test set. So this test set is a high current circuit breaker and overload relay test set. It is designed to test the circuit breaker by means of primary current injection.
Okay, now let's start the experiment. In this experiment, we are going to use this mega test set and try to inject different current values into the MCB and see how fast the circuit breaker will trip. So this is the mega test set. This is the power button. And we will connect the circuit breakers using these two terminals. And for the setting of these two panels, you can remain them unchanged. And we will use this button to start the current injection. And the magnitude of the current can be adjusted by this knob. So these are the three circuit breakers we are going to test. All of them have the same current rating of 6 amp, and we have type B, type C, and type D miniature circuit breaker. The first circuit breaker we are going to test is the type B rating 6 amp MCB. So first of all, we connect the two ends of the MCB to the terminals of the mega test set. We turn on the MCB. This button should be at the off position before we turn on the mega test set. Then we can adjust the knob to change the current value while pressing this button to the momentary position. So for the 6M MCB, we may start with a current values of around 2 times of the rating. The current value is now around 11 amp. Now we can start the current injection by pressing the button to the maintain position. So a current of around 11 amp is now injecting to the MCB. So we just wait until the MCB trip. We just heard the click sound. It means that the MCB has been tripped. We should press the button to the off position. The display shows the current and the disconnection time, 18.65 seconds. You have to record down this set of data. And then we need to wait for 1 minute for the circuit breaker to cool down. After 1 minute, we can turn on the MCB and try another current value. The button is still at the off position. Then we can directly turn the knob a little bit to increase the current magnitude. We press the button to the maintain position to start the current injection. You can see that this time the current value has been increased to around 12 to 13 amp. And after that, we have to wait until the MCB trip. So we just heard the click sound and the MCB has been tripped. So once again, back to off position, and we have to record down the data and wait for 1 minute. After the MCB is cooled down, we can try a larger current value. And for larger current value, the disconnection time would be shorter and shorter. So for a current value of 14.6 amp, the disconnection time is around 8 to 9 seconds. So we need to cool down the MCB once again and repeat the procedures for other larger currents. For current of 16 amp, the disconnection time is 7.74 seconds. And we repeat the procedures for other larger current values until the MCB trips instantaneously. That is, the disconnection time is less than 0.1 second. So I am now repeating the above procedures for many more sets of data until the disconnection time is less and less, and then finally less than 0.1 seconds. This is the last set of data for type B MCB, and you can notice that once I press the button to maintain, the MCB trips very fast, less than 0.1 seconds. So this is the last set of data. You have to record it down, and then we can switch off the mega test set and start the testing for type C MCB. So this is the type C6M MCB we are going to test. So we switch on the MCB, and the button should be at the off position. We turn on the mega test set, and then while pressing the momentary button, we turn the knob to adjust the current value. Press the button to the maintain position to start the current injection. And we wait for the MCB to trip. So we just heard the click sound. The MCB is tripped back to the off position, and wait for 1 minute for the MCB to cool down. And after 1 minute, we can just repeat the procedures for larger current values, just like what we have done for the type B MCB. The MCB has just tripped instantaneously, so this is the last set of data for the type C MCB. Now we can do the same testing for the type D MCB. We follow the same procedures, turn on the mega test set, and we press momentary and adjust the required current value. Then press maintain and inject the current to the MCB, and wait for the MCB to trip. We heard the click sound and the MCB has just tripped. So once again, record down the data and wait for 1 minute for another measurement. And we repeat the above procedures for larger current values until the MCB trips instantaneously. The MCB has just tripped it instantaneously. So this is the last set of data for the Type D MCB. These three tables summarize all the measurement data for the Type B, Type C, and Type D MCB. You may plot these data onto the graph to see if they comply with the British standard. In this experiment, we have used the miniature circuit breaker to do some experiments. And in the laboratory, we have a sample of MCCB. The brand of this MCCB is also Schneider. You can see that the MCCB is much bigger and heavier than a MCB. And there are different settings you can use to adjust the instantaneous tripping current of the circuit breaker. The second stage of this experiment is to test the tripping characteristics of the residual current device. This is the residual current device that we are going to test. And there are two conductors connecting to and out of the RCD. It is because a residual current device will monitor the instantaneous current flowing along not only the line but also the neutral conductors. You may refer to this circuit diagram for the wiring connections. In this setup, this socket outlet is protected by this RCD. Now we are going to power this setup by connecting the plug to another socket outlet which will supply the electricity. And we have to connect the power through this isolating transformer. This is the RCD tester we are going to use in this experiment. And the testing procedures of using this tester is shown here. There are only a few buttons on the tester. The RCD is now at the off position. Now we can press the test on button to turn on the tester, and then we can press the test on button again and press select to select the time delay mode. Press the test on button again and adjust the dial of current adjust button. The first testing current value will be 15 milliamp. Then we turn on the RCD. These two indicators should be on. Then we press the test on button twice to start the test. And a residual current of 15 milliamp is now being tested for this RCD. And we will wait for the RCD to trip. As shown on the screen, the RCD didn't trip for a time longer than 20 seconds. So we can record that for a residual current of 15 milliamp, the RCD will not trip. We should turn off the RCD. Press the test on button twice and press select button to choose the time delay mode. Press the test on button again and adjust the dial to a current value of 30 milliamp. Then switch on the RCD and press the test on button twice. The RCD has just tripped with a disconnection time of 0.032 seconds. Make sure the RCD is in the off position, and we repeat the above procedures for larger current values. The next current value is 30 milliamp. You may need to spend some time to adjust the current to the exact value. Then turn on the RCD again, press the test on button twice. The RCD has just tripped and the display shows the disconnection time. Repeat the procedures for larger current values. The next setting is 100 milliamp. Turn on the RCD and press the test on button twice. The RCD trips very quickly, and the disconnection time is shown on the display. We repeat for another current value, which is 150 milliamp. For a residual current value of 150 milliamp, the RCD trips in 0.037 seconds. The last testing current value is 300 milliamp. And the same procedures are repeated. For a residual current value of 300 milliamp, the tripping time is 0.03 seconds. And this is the last set of data. After collecting all the data, you have to refer to the British standard BSEN 61008-1 to check if the performance of the RCD has complied with the requirements. You may refer to Table 1 of Section 5.3.12 and also Section 5.3.4.